Welcome everyone to the 2023 Photonics Spectra Summit Series. Thank you for attending our Infrared Optics Summit, and in this session you will hear from Nassim Asida, the Director of Engineering, Research and Development at Ophir Optics, an MKS brand. Nassim earned his doctorate in nonlinear optics and lasers and has roughly 30 years of experience working with electro-optics. Today he'll share how to optimize next-generation IR thermal imaging systems and applications. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. Nassim, we appreciate you for taking the time to join us today.
Thank you, Jacob. I'm honored to participate in this summit. And the topic of my presentation is unlocking the future of low-SWaP thermal imaging, design challenges, and performance. I will start my presentation with one slide describing MKS Ophir Optronics and then give a short introduction to thermal imaging, followed by current trends and application drivers. Next, I will describe the main lens requirements for advanced applications involving thermal imaging and explain the correlation between optics quality and detectors. Then I will elaborate on the many challenges we face in terms of optical design, mechanical design, and manufacturing, and then explain how we address those challenges. Next, I will present some of Ophir's advanced low-SWaP zoom lenses and demonstrate their performances, and finally conclude with a brief summary. Ophir MKS designs and manufactures optics and optical assemblies, especially, but not only, infrared optics for all markets, defense, commercial, and industrial. In the commercial market, Ophir's products are used for thermal imaging and are integrated in a variety of commercial applications, offering innovative, cost-effective solutions for high-volume, lightweight infrared optics. In the defense market, Ophir MKS is a leading provider of high-quality infrared optical components and assemblies for sophisticated military applications with decades of experience in meeting defense standards in terms of quality. As for the industrial market, Ophir MKS serves the industrial high-power laser material processing manufacturers and users, delivering the highest quality components and assemblies for both fiber and CO2 lasers, cutting and welding machines. Ophir MKS is recognized as a technology leader in delivering innovative, high quality and reliable solutions with over 40 years of experience, cutting edge design and manufacturing capabilities, as well as military credibility. Ophir's comprehensive portfolio includes a large variety of optical components and lens assemblies. Ophir MKS is known as one of the highest quality optics companies in the world and is ISO 9001:2015 certified, and also has the AS 9100 aviation quality standard. Introduction to thermal imaging. All objects at temperatures above absolute zero emit infrared radiation in the 3 to 14 micron wavelength range. The higher the temperature of an object, the higher the spectral radiant energy or emittance is. Thermal imaging cameras record the intensity of the radiation in the infrared part of the electromagnetic spectrum and convert it to a visible image. Thermal imaging is very popular today in commercial and security systems such as autonomous cars and ADAS, which is Advanced Driver Assistance Systems, agriculture, thermal mapping of power plants, gas plants and pipelines, traffic monitoring, as well as infrastructure security systems and many more. In this slide, we show the basic elements of a thermal imaging camera. Starting from the scene, we would like to image The electromagnetic radiation emitted from the object is transmitted through the atmosphere to the infrared lens, which collects the radiation and focuses the image of the object on the focal plane array in the detector module. The detector module converts the infrared signals to electronic signals, which are then processed through noise reduction and signal improvement to display the final image on the monitor. The most important feature of any thermal imaging system is its ability to detect, recognize, and identify various objects in the scene. The detection, recognition, and identification, or DRI, ranges of a thermal imaging system depend on many parameters, which include detector type and spectral range, pixel pitch, detector sensitivity, lens focal length and F number, lens image quality, which is related to the modulation transfer function, or MTF, atmospheric transmission, background temperature, and target size and temperature. As for trends in the infrared thermal imaging systems, we can see various and sometimes even contradicting trends. On one hand, we observe a growing use of small UAVs, which is unmanned aerial vehicles, drones, and handheld lightweight systems. But on the other hand, a strong demand for long-range, all-weather security and surveillance systems. Consequently, large UAVs and drones used for military and security require some specific demands from the optics, namely increased operation ranges, while smaller drones for commercial use present greater SWaP constraints, where SWaP stands for size, weight, and power consumption. Another major trend is increased camera detector resolution and format and decreased pixel size. In summary, we can see strong requirement for high performance, low SWaP optics suitable for small pixels, long range detection, constrained platforms operating in harsh environmental conditions. I would like to elaborate on the lens contribution to the mission success. Firstly, we must understand that advanced detector resolution will not improve imaging performance without an improvement in lens quality. In an optics limited system, an inferior lens will produce an inferior image, even with the best detector. Secondly, to match high performance detectors, lower F number and tighter tolerances are required in order to obtain lenses with minimal aberrations. Also, lenses must have a long focal length and high image quality for maximum target detection ranges. In summary, the main lens requirements for advanced applications are high quality imaging, which means high MTF performance, low SWaP design, long detection ranges, or in other words, long EFL, focal length, high zoom ratio, high optical transmission, low distortion at all zoom positions, high relative illumination across the full field, athermalization, full performance at harsh environmental conditions, which means extreme temperature, shock, vibration, and also long lifetime. The above requirements present many challenges on both the design and manufacturing of advanced infrared zoom lenses. In terms of optical design, the main challenge is to achieve high MTF performance under many constraints, such as large zoom ratio, high spatial frequencies, large detector formats, short total track, high sensitivity to tolerances, athermalization, and narcissus-free along the full zoom range. In terms of mechanical design, the main challenges are lightweight design, accurate zoom and focus motions, resistance to shock and vibrations, tight decenter and tilt requirement, no backlash requirement, athermalization, and wide temperature range. And as for manufacturing and assembly, tight tolerances for all optical components, which means low irregularity and power, tight thickness tolerance, small ATV, etc., tight decenter and tilt requirements, tight line of sight and bore sight requirements, and precise alignment and calibration processes. So how do we address these challenges? One of the best practical solutions for thermal imaging optics for low-SWaP applications is the use of continuous zoom lenses, which reduce lens size and weight while keeping high performance and better mission flexibility by allowing changes in magnification during operation. I would like to emphasize that a single zoom lens is smaller and lighter than using multiple single field of view lenses. Now, I would like to elaborate on Ophir's infrared low-SWaP zoom lenses. First, how do we meet the low-SWaP goals? Well, we do it by combining several methods, including innovative optical and mechanical designs, as well as cutting-edge production and assembly technologies. In terms of optical design, we use advanced infrared materials which with aspheric and diffractive surfaces for reducing spherical and chromatic aberrations while keeping the number of elements at minimum. We use also near diffraction limited designs, thermal designs, folded optic configuration to reduce size and weight, and fixed F number, which is maintained through the full zoom range. As for mechanical designs, we use advanced materials for thermalization, low size and low weight. The focus in our designs is maintained through the full zoom range. We achieve fast zoom and focus motions. The designs ensure tight bore sight and low power consumption, as well as wide operational temperature range and high durability to harsh environmental conditions. Finally, we utilize our cutting-edge production technologies, which include spherical, aspheric, diffractive, and freeform surfaces, tight manufacturing tolerances, large optics manufacturing capabilities, and high durability and low reflection hard carbon anti-reflection coatings. Now, I will present few products which demonstrate the above-mentioned challenges and solutions. The first lightweight product is our 275mm f5.5 zoom lens. This lens is the smallest, lightest, and the most compact lens of its type on the market, with operating temperatures range from -35 to +70 C. Compared to our older 19 to 75mm lens, the new lens weight has reduced from 445 gram to 264 gram, which is more than 40% reduction. Lens dimensions have been also significantly reduced to satisfy low-SWaP requirements. Now, what about the optical performance of the lightweight design? As can be seen from these graphs, the MTF performance is close to the diffraction limit in the narrow field of view along the entire image frame, while for the wide field of view, the image quality is still high, but slightly degrades as we approach the image corners. Actually, this high-level MTF performance is maintained over the entire zoom range and over the entire operating temperature range. Now let's see a short video demonstrating the zoom performance of this lens. The second lightweight zoom lens is our 18 to 25 mm f3.6, which was designed for advanced SXGA 10 micron MOV focal plane arrays. The main characteristics of this lens are lightweight lens with 300 gram only. F number and focus are maintained through the entire zoom range with tight through zoom bore sight. Unique athermalization and achromatization concepts, and wide operating temperature range. To appreciate the advantages of this lens, let's compare between this new lens to one of our most popular lenses, which is the 15 300 mm lens. As you can see from this table, the F number for the new lens is smaller, which means that the signal is 23% higher. The FPA format has 4x more pixels, while the pixel pitch is 33% smaller. The wide field of view is 16% wider, while the narrow field of view, instantaneous field of view, is 12.5% smaller, which implies longer DRI ranges. Both diameter and length are significantly smaller, and the most impressive swap reduction is in the lens weight, which was reduced by no less than 70%, from 965 grams to 300 grams only. The message here is that by using this lens, you get higher DRI ranges with much lower swap. The next lightweight product I would like to present is our long-wave infrared 1575 mm zoom lens for uncooled detectors. As discussed earlier, one aspect of the continuous progress of infrared detector technology is reduced pixel size. The new generation of uncooled infrared detectors has a pixel pitch of 10 to 12 micron, which is much smaller than the 17 micron pixel pitch of the previous generation. Utilizing this reduction in pixel pitch, we designed the 1575 mm zoom lens for the new generations of detectors in such a way that it will yield the same performance in terms of operational ranges as our older 26 to 105 mm zoom lens, which was designed for the previous generation 17 micron pixel detectors. Consequently, we succeeded to reduce the lens weight from 575 grams down to 320 grams, which is 44% reduction. Similarly, the physical lens length was shortened from 125.5 millimeter to 88 millimeter. In short, the new lens design provides the same field of view angles with significant swap reduction suitable for small pixel FPAs. I will play now a short video demonstrating the performance of this lens. I would like now to talk about folded optic lenses. Folded optics means that we fold the optical axis by using total reflectors. The motivation and core requirements in folded optics designs are to shorten system overall lengths while maintaining a long focal length, long optical lengths for reduced sensitivity to tolerances, efficient volume utilization, and compact design, which is ideal for low-SWaP systems. Main challenges when designing folded optic systems include complicated optical design, complex integration, complex line of sight calibration process, extra optical elements within limited volume, and weight and image tilt. The use of folded optics enables the creation of ultra-compact electro-optical systems, mainly gimbals, with unparalleled image quality. Such technology paves the path to incorporating a large aperture lens with long effective focal lengths and extended vision ranges, while minimizing the total size of the payload gimbal. Reduction in size is accomplished by double folding the lens optical axis back on itself by two reflecting mirrors at 45 angle of incidence, significantly reducing the overall length of the infrared lens. Typical zoom lens designs are characterized by a train of several lens elements in which the front element has the largest diameter. In such case, the largest lens diameter determines the diameter of the payload gimbal, whereas in folded optic design, the height and width of the overall lens assembly are reduced. The last lens I would like to describe is our 16 180mm f3.6 zoom lens for medium wave infrared. This is a folded optics zoom lens, as can be seen here. I would like to mention that the solid model shown here includes the detector module with its cooler, and to emphasize that this feature of compact system design was made possible only due to the folded optics design. Key features of this lens are medium wave spectral range of 3.6 to 4.2 micron, FPA format VGA 10 micron pixel pitch, 11x zoom ratio, high image quality, and small footprint, which is SWaP compatible. The following slide describes the nominal MTF performance of this lens in various zoom positions. As can be seen, the optical performance is close to the diffraction limit in the entire image frame and over the full zoom range from wide to narrow. Let's see now a short video demonstrating the images captured by this lens. I would like to conclude my presentation with the following summary. Modern thermal imaging systems require reduced SWaP, high-quality optics. Many challenges must be addressed to meet all requirements of next-generation optical systems. Advanced low-SWaP infrared zoom lenses are based on innovative lightweight designs suitable for small pixel FPAs and long-range detection. Long EFLs are required for long-range applications. Zoom lenses are ideal for many applications, such as UAVs, handheld and small gimbals thermal imaging applications, enabling high mission flexibility, small SWaP, and long ranges simultaneously. Folded designs offer many advantages, but are challenging. Such lenses open up new opportunities in next-generation UAV, handheld thermal imagers, and small gimbals thermal imaging applications. Ophir offers excellent optics design and manufacturing capabilities, as well as a large variety of existing zoom lenses for the next-generation thermal imaging systems. And with this, I would like to conclude. Thank you very much.
Thank you so much, Nassim, for joining us to discuss advanced folded optics and lightweight zoom lenses. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the conference chat, and do not worry, if you have not been answered it, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the inaugural Photonics Spectra Summit. Thank you all so much for joining us.